Hey guys, so we're going to do refraction today. Again, your notes packet that you've been following along with cut off, I think, right before this section. So if you look in Google Classroom and you look at this workbook right here, attachment, then you should be able to find where we left off. I think it's on page 14. Page 14, so scroll all the way down. Page 14 is right here. Okay, we're going to start with 8.5 notes, lenses, and refraction. We just did mirrors. So we just did convex and concave mirrors and the mirror equation. And lenses are pretty similar with a couple of differences. And there's going to be concave and convex lenses as well. So again, refraction. Now, y'all remember that refraction is when we have an object going through, or light going through two different mediums. So air to water is one we're all very familiar with. And the light still passes through, but it changes direction. That's how you have the phenomenon of a pencil that ends up looking kind of broken when you put it into water. And it looks like it's kind of like bent or something. All right. So that is the light that is passing through is still going from one medium to another, but it's just changing direction. Okay. So refraction. Again, change in direction of a wave passing from one medium to another. And here we go. Here's the pencil right here. Pencil trick. The speed of the wave actually changes too. So light, unlike sound, sound travels faster and faster the more dense the medium is. So, you know, sound through metal is going to be like 5,000 meters per second, depending on the metal. We all remember that from our musical instrument project. And then sound through air is much slower, and sound through vacuum doesn't even exist. But light acts differently from that. Light travels very, very fast through a vacuum, the fastest, in fact, through a vacuum. And then as it enters air, it goes a teeny tiny bit slower. As it enters water, it goes a little bit slower. And then you have like the most dense medium, like a diamond, where it will travel the slowest. So the more dense the medium, the more closely packed together that those atoms are, the slower light will travel. So this is called the index of refraction. It's a ratio, basically. It means, you know, how much slower light is going. So we can see right through here, a vacuum, it's just 1. The speed of light at full capacity. And do we remember the speed of light? Yes, the speed of light is 3 times 10 to the 8th meters per second. So in a vacuum, we are saying that it's 3 times 10 to the 8th meters per second. In air, we are saying it's just a teensy bit slower, but it's 1.00028. It's so insignificantly slower that we'll still just use 1 as our index of refraction. Okay, it's so insignificant that we can't even really see it. But water, it is a little bit slower, and we can see that, we can actually visually see that. We can see that light slows down, changes direction as it goes from a fast from air to water, because it does go a little bit slower. And then glass is even slower than that. You go to a diamond, it's even slower than that, okay? So again, the larger this number is, so the greater that n is our index of refraction, the greater n is, the slower light will travel. The slower light will travel. The closer it is to 1, the faster it will go. So refraction on a plane surface. Again, we have 2 different mediums, medium 1 to medium 2, and we can assume this is probably from air to water. We have another normal line. This is a line for reference. to, figure out at what angle our incident ray is coming in and what angle it's going to refract. Obviously, our refracted ray is the one that is going into the second medium. Okay, and you can probably assume that we're going to start solving for something. So you need two different indexes of refraction, N1 and N2, and that specifically has to deal with the medium that it's traveling through. So your first medium is where your incident ray is. So if it's air, then your index of refraction is going to be what? It's going to be 1. Okay? No, you don't need to remember these. You'll probably be familiar with air because it's 1, right? It's very, very close to 1, so that's why we just say it's 1. Remember from our, here, air is 1.00028. We're just going to use 1. And then water is 1.33. So if we are going from air to water, then our N2 is going to be 1.33. Okay. And if we know what two mediums the light is going into and then refracting into, and if you know one of these angles, like if our incident ray, if light is traveling at, 45 degrees in air and then it enters water, what is the angle in which it will refract? And you can figure that out. You can figure out exactly what angle at which it will refract in the new medium. So when we have a plane surface, and this just means a very straight surface that light is refracting through, okay? The greater the difference between the indexes, the more drastic the light wave will bend. And that just means, like, if it's going from a vacuum, if we could somehow get light to refract from a vacuum to a diamond, it is going to bend so significantly versus if it were to just travel from a vacuum to air. Okay, so the greater the difference between those N numbers, the more that light is going to bend. The faster the medium to the slower medium, it's going to bend towards that normal line. So that means here, this normal line right here. So if it's going from a very fast to a very slow, to a slower medium, then it will, as it comes through, it's going to bend closer. It's going to try to stay to this y-axis right here, the normal line. Okay. If it's going from a slower medium to a faster medium, so if we have light that is escaping water, if we're going from water up to air, then you could kind of just reverse these, then it's going to bend away from the normal line. So your reference would kind of be the x-axis instead. Okay. So these are some examples of different index refractions. So you don't need to remember these, and again, you'll have, the internet at your disposal when you are quizzing and testing over these things. So I would be giving you whatever medium, I would tell you what medium you're in, I'd give you this index, and you would be able to look up what your N is. But just look at these numbers for a little bit. So I was wrong, I thought diamond was the most dense material that light could go through, but gallium phosphide is even greater. What is gallium phosphide? Let us Google that. Gallium phosphide. Gallium phosphide. Gallium phosphide is compound semiconductor material. Polycrystalline material. Interesting. I wonder what it's used for. Semiconductor. Okay, well, there you go. All right, so regardless, that is a very, very great number from 1. Again, vacuum, that's absolutely no particles or very, very few, is 1. Air is a little bit more. Carbon dioxide gas, a little bit more, but barely, that's important because our air right, is filled with a lot of carbon dioxide and nitrogen gas, and it's still 1. Ice, a little bit thicker. Quartz, vegetable oil. Okay, so you get the gist. All right, this is our formula. N1 sine theta of 1 is equal to N2 sine of theta 2. So this whole part of the formula is to deal with the first medium, usually the incident medium. And then this part of the formula is the refracted one. So if we are going, like our example that we've been using from air to water, then this would be air and this would be water. Okay, our N1 would be 1. This would be whatever angle they give us that the light is entering. And then usually you are finding the theta, or maybe you have a mystery material, a mystery medium that you're going into, and then you would solve for N2, okay? So you'll have 3 out of 4 of the unknowns. Okay, let's do this example. So we have a light beam in air, hits a sheet of glass. So we're going from air to glass at an angle of 30 degrees. At what angle is the light beam refracted? So we have air, that's going to be our N1, to glass, that's our N2. We have our incident ray, so that's going to be theta 1. And we're looking for theta 2. Okay, let's rewrite our formula. Let's see if I can zoom in. Perfect. So our formula, again, was N1 sine theta 1 is equal to N2 sine theta 2. So N1 was for air, and our angle was 30 degrees, is equal to N2, and I don't remember what glass was, so let's go back and look. Glass was 1.52. So let's come back here and put that in. 1.52 for glass, and sine of theta 2. So we are trying to figure out, we're going from air to, not water, glass. This is our normal line. Angle's going this way. So this is our incident ray. Okay. And now we're trying to figure out what angle it bends. So that's going to be this one. Again, if you're going from a fast to a slow medium, then it's going to bend towards the normal line. That's your normal line, that one right there. All right, so let us solve for that. Let me erase this. So sine of 30 is 0.5. It's equal to 1.52. Sine of theta 2, divide both sides by 1.52. 1.52. And you should get 0.3289. 0.3289 is equal to sine theta 2. And now in order to solve for the angle, you have to do the inverse sine in order to figure out what that is. So that's this kind of function in your calculator. All right, and when you do that, you should get answer of, zoom out all the way, zoom out, zoom out, zoom out. Answer of 19 degrees. So theta 2 is 19 degrees. All right, moving on. Now, sometimes you might need to calculate what N actually is. If I were to tell you whatever velocity you have going on in the new medium, and this is how N is derived. So we already talked about the velocity of light in a vacuum. You know that that is 3 times 10 to the 8 meters per second. But let's say, I don't know, velocity of light suddenly changes to 1 times 10 to the 8th meters per second, in which case your N would be the ratio between them. So it would be 3, okay? So moving from a slow medium to a fast medium, there's a possibility of reflection, where reflection is bouncing off of something. So if you have water and air, and let's say you have a laser underneath the water and you're trying to get it out of the water and into the air, there's a possibility of some backfiring or some reflection bouncing off of that boundary between the mediums. So this is called there's a critical angle. Basically, there's a maximum angle that the incident ray can be before it can no longer exit the slower medium, and it's totally reflected inside, a total internal reflection. So this shows that if we're going from water to air and you have a laser underneath the water and you're trying to get it to exit, the greater the angle, the more internal reflection you're going to have. So if you see these exit refracted rays right here, 0 degrees, it's going to be very, very dark, very close to what color it is and the brightness of when it's inside water. As you increase that angle, so as you go from 15 to 30 to 45, you start to see this little green arrow right here, and that's showing reflection, internal reflection. So it's coming up to the border between water and air, and it's reflecting. Now some of it is still escaping, the majority of it is still escaping, until we get closer and closer to 60 degrees, which now we don't have anything reflecting or refracting, nothing is leaving, and we have total internal reflection. Total internal reflection. So how can we calculate the angle, the critical angle, to where, the angle in which your light cannot escape the medium? So it depends on what the medium is. We have light, so is the medium very, very thick, in which case you're going to it's going to be harder for light to leave at greater angles than, if it's something that is not very dense. All right, simple equation, sine, inverse of sine is equal to n2 over n1. All right, and it's important to remember that n1 cannot be greater than n2. So if you were to actually, let's do this one. We're going to calculate the critical angle of a ray going from olive oil to air. Olive oil to air. So we need to figure out which medium olive oil is going to be and which one air is going to be. So if we go back to our index of refraction, we can find olive oil right here is 1.48. So let's make olive oil N2 and air N1. N1, N2. So air was 1 and olive oil was 1.42. So our formula was to find the critical angle with sine inverse of N2 over N1. And if we were to plug in inverse sine 1.42 olive oil over 1, and if you were to plug that into your calculator, so second sine 1.42 divided by 1, I am going to get an error, domain error. So you can't do an inverse sine of something greater than 1. So if you were to get that, that's going to tell you need to switch them. So N2 cannot be greater than N1. So basically you have to switch these two guys. Okay? Otherwise it doesn't work. So your slower medium is going to be on the bottom and your faster medium will be on the top. So N2 will be fast over slow. Okay? So now our N2 is going to be air and our N1 will be olive oil. And if you do sine inverse of 1 over 1.42, then you get an internal critical angle of 43 degrees. So this means that that's our critical angle. This means that if I'm going from olive oil to air and I'm shining a laser pointer from olive oil to air, the critical angle in which there will be total internal reflection and nothing will leave is 43 degrees. That's what that means. These are some extra practice problems for Snell's law, which was going from one medium to another. Remember, this was Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. And index of refraction practice and critical angle practice. So this is in page 17 of your workbook, which again, if you are able to print, I would highly suggest that you do that. This is where it is right here. And these are the practice problems. So I'm just going to put the answers on here for you really quick so that you can know if you're getting the right answer or not. And I'll post the solutions as well. There you go. Those are the answers right there for each one. Okay. Oh, and I also forgot to note that polystyrene right here, that's not in the table that I've given you for what its index of refraction is. So polystyrene, the index of refraction for that is 155. Okay. Okay. Now we're going to compare and contrast convex and concave lenses. I'm going to try to go through them quickly. So we've been doing mirrors, which mirrors reflect. Now lenses refract and either focus or spread out light. Convex lens focuses light. So it's also called a converging lens because parallel rays converge towards one another or come together towards one another. So an example of a convex lens that we are all familiar with is a magnifying glass. So as you are looking at an object, the light that is coming through right here is going to go through our lens, which is usually glass or plastic, and it will bend and refract as it goes through one medium, as it goes from air to glass, and we'll focus on the other side. All right, and it's important to know that in this case, when we are looking at lenses, the viewer is on the opposite side of the object. And I'll explain that in this next one right here. Okay, so the virtual side and the real side are flipped for lenses versus mirrors. So virtual side is going to have the object, and our real side is our viewer. Okay, and this is my eyeball to show that the viewer is right here. Because when we look at objects with a lens, we look through the lens at the object. Okay, we look through the lens at the object. So with a convex lens, let's say that this was like a magazine and it's really small and we need to blow it up and make it bigger. Then you are going to put that lens in front of the object, if it's a magazine, and you're going to look through it. So you will look through it that way. Okay, if the image were to pop up on this side, up or down, then it'll be a real image, and if it pops up on this side, then it will be a virtual image. Okay. So if the image is on the same side as the object, then it's virtual. And if it's on the same opposite side or on the same side as the eyeball, as you, then it is real. So drawing ray diagrams for a lens. It's very similar to a mirror. We're going to do convex lenses first. First, you're going to draw a line from the top of the object straight to the lens. And then you will connect it through the primary focal point F. Now, there's going to be two focal points instead of just one, like with mirrors. But you're going to connect it through the primary focal point. And you're going to draw a line from the top of the object straight through the center of the lens. And images form where they meet. So this shows that first one. So if we have an object that is past the focal point, so this is going to be the primary focal point, this is the secondary focal point, okay? For a converging lens, convex lens, this is the focal point that it will go through. It's going to focus on the opposite side. All right, so this is the viewer, the eyeball. Light is coming through here. It's going to go straight to the middle of the lens, and now our principal axis is going to be right down the center of our converging lens. Okay, it's going to go straight to that line right there, and then it will connect through F. So that's the first one. Now we're going to do top of the object straight through the center of our lens right there. Straight through the center of the lens. So in some cases it's a little bit easier to draw these than with mirrors because you don't have to worry about the radius or the center of the mirror, geometric center of the mirror, or anything like that. You just have to worry about being parallel to this line for the blue line and then going straight through the center of the mirror for that one. And then where they intersect, which is right here, is where your image will be created. So our image is right there. Now, do y'all remember what salt is? It's what describes our image. So S would be the size, and it is smaller than our object. A would be the attitude. It's inverted. It is on the same side as the viewer. So location would just be maybe opposite side, opposite of object. And then T, type, since it's on the same side as the viewer and it's inverted, that should tell you that it is real. Same side and inverted, that should tell you that it is real. Okay, let's do this example. So first, we probably need to add a principal axis down the middle, somewhat in the middle. And now we will do our first line. So with this one, it's going to be different from our example because our object is in between the secondary focal point and our primary focal point, which is this one. Okay, primary focal point, converging lens, convex lens. This is the viewer, right? Viewer is on the opposite side of the object. Okay, because you look through a lens at an object. So our first line is going to go from the top of the object straight to the middle of the lens, and then it will go through focal point, the primary focal point. And then we're going to switch and go from top of the object straight through the middle. Now if I keep going and drawing it this way, then they're never going to meet. They're just going to get farther and farther apart. So what we do is we're going to, if they're never going to meet on this side, then we will extend our lines back this way and see if they meet on the other side. And it looks like they'll eventually meet on that side. And we would have an object form over here. Okay, so salt for this one, size would be larger. Attitude would be upright. Location would be beyond f prime on the virtual side, and thus the type it is virtual because it's on the other side of the viewer, on this side of the viewer. All right, let's do this one, where now our object is past f prime. I'm going to make this a little bit smaller, just in case it goes. Okay, so again, let's add our principal axis in the middle. Remember that viewer is on this side, and if the image pops up on this side, it will be real. If it pops up on this side, it will be virtual. First line goes from top of the object straight to the center, and then through our primary focal point, f star. This is the secondary focal point. And our second line will go top of the object straight through the center, and it will form over here. Okay, so size should be larger, inverted. Location would be beyond f prime, or f primary, and it is real because it's on the same side of the viewer. All right, concave lenses. Concave lenses. They are diverging lenses because as light is coming through, it will spread out and refract out. All right, so concave lenses cave in, so they still have the same shape as a concave mirror. All right, that just describes this outward part right here that's facing the object. They're going to spread out, diverging. So examples of this would be a type of magnifying glass that doesn't magnify, but makes things smaller. So if you were to look through, basically if you were to look through, it's like a demagnifying glass. If you were to look through one of these concave lenses, then it would make things smaller. Okay, it does form virtual, smaller, and upright images. These concave lenses act like a convex mirror in the sense that they will always form the same type of image. They will always form a smaller, upright, virtual image, just like a concave or a convex mirror does. So, same thing, virtual side. Real side is where the viewer is. You look through a lens and at the object, okay? And the image will always form on this side of the lens because we said that you will always get the same type. You'll always get virtual, smaller, and upright. If you have an image that forms on the real side, then it will be upside down and it would be on the same side as our viewer. Okay, but since they always form virtual images, then they're going to show up on this side really tiny, small, and upright. Always, always, always. So I'm going to show you how to draw them. It's very similar to how we drew the convex ones. So you still draw a line from the top of the object straight to the lens, and then you'll refract it through the primary focal point, which is now on the same side. You'll extend that ray through the primary focus point, and then you'll draw a line from the top straight through the center. So only real difference between our concave lens and our convex lens is these blue lines. And it's not really that different, but I'll show you what's happening. Okay, so if we have an object through that we're looking through a concave lens, which remember concave lenses, they diverge light. You will draw an object, or you will draw your line from the top of the object, straight line to the center of the lens, and then it's going to refract at an angle. Now, how do I know exactly what angle that's going to refract at? Well, if I had a ruler, I would line it up with my primary focal point, which is this one now. So it's on the same side as the object versus convex, it was on the opposite side. Remember, the viewer is on this side, Okay, so this is the real side, and this is the virtual side now over here. Okay, now why do I have these dotted lines? That's because that's where the light appears to go. It's not where it actually goes. This is where the light would actually go. And if real light were to converge on this side, then, real light were to converge on this side, you would have a real image. But since it appears to form on this side, we have dotted lines. Okay, so we have dotted lines. That's just to reinforce the fact that it is going to create a virtual image. All right, so that is a straight line that connects with this first line from the top of the object straight to the mirror. And then you have your ray that is extended through the primary focal point. Now, our third line, same as with convex. Top of the object straight through the center right there, center of the lens. Okay, and then where does the image form? Image should form right here where they meet. All right, because they're never going to meet on this side. See, the red and the blue, they're just going to keep spreading out. They're only going to meet right here where they appear to meet because we have a dotted line. So you have a tiny little image right there. It will be virtual, smaller, and upright. And that's what we have. Smaller, virtual, upright. Okay. Again, concave lens, you will always, always, always get that. It is like a convex mirror. It's just like a convex mirror. Concave lens is like a convex mirror. You'll always get a smaller, upright, virtual image, virtual image. So it doesn't matter how we orient our object, if it's in front of the focal point or if it's behind the focal point. What we can see is it will still create a smaller, upright, virtual image, but I will show you how that happens. So top of the object straight to the middle of my lens, that principal axis, and then this is our primary focus point. This is the secondary one. So now I'm going to do a dotted line that lines up perfectly with that one. Dotted line goes through here, and then straight line this way. If the dotted line confuses you, just do a straight line, that's fine. And now we have a red. It goes straight from the top to the middle, and our two objects, our two lines will meet right here. See, still smaller, upright, and it is virtual because it's on the opposite side of the viewer of our eyeball. Let's do this one. Again, this is F prime, this is the secondary one. Top of the object straight to the center of our of our lens. And I would highly suggest you use a mirror or a ruler for this so you get better lines than what I'm doing right now because I'm just freehanding it. All right, top of object through there. They meet right there. Again, it's smaller, upright, and virtual. You probably noticed I'm leaving the location out of my SALT, my description for this, because it's pretty much, it's going to be the same every time, right? What's important to know is that diverging lenses, concave lenses are diverging and they will always create virtual, smaller images. All right, summary chart. So this summarizes both of the types of lenses, concave versus convex. So concave, remember, looks like this. That's a concave mirror, or lens, I'm sorry, lens, concave lens. And this is a convex one. So this is a magnifying glass. This is, concave is kind of like what you would use, like a peephole on a door where you can see people, it's upright, but they're like kind of a little bit smaller. They take things, they're good for using a lot of, taking a lot of light in and like narrowing it down, making it smaller. So peephole in a hotel door room, or in a hotel door would be an example of a concave lens, and then a magnifying glass is a convex one. Our eyeballs have convex lenses in them. They form real images on the backs of our retinas, and they're actually upside down, and then your brain flips them. It's kind of interesting. So, all right, concave type of image. It will always create virtual. Object distance, it can be any distance, does not matter, and the size will always be smaller and upright. But convex can do both. They can do virtual and real. If the object is between F and the lens, then you're going to have an enlarged upright image. If it is between 2F and F prime, so 2F, that's just like 2 lengths away from the focal point. It's just saying if the object is really, really far away from the lens, then it is going to be enlarged and inverted in a real image. And again, if it's even farther away, like really, really far away, it'll be smaller and inverted. Some of you guys might have remembered when we were playing with lenses and magnifying glasses in class forever ago, when we were doing that discovery lab with light at the beginning of this unit, that I saw some of you guys when you were looking through the magnifying glasses and you took them very far away and you were looking at them. And if you have a magnifying glass at home, I don't know if you do, but if you look through it and you move it really far away from text or anything like that, it actually does flip upside down, which is kind of weird. But yeah, so you have to be a certain distance away from a convex lens in order to have that real image occur. All right, last thing to know for this unit, and I'll try to go fast. I'm sorry, it's I know that this is a longer lecture than we're used to, is the lens equation, and it's just like the mirror equation. So this shouldn't be anything terribly new. So just remember, with mirrors, the virtual side was behind the mirror and the opposite of the object, and the real side was on the same. But with lenses, with a lens, it's switched. So the real side is where the viewer is, and the virtual side is where the object is. Okay, so this is the negative side and this is the positive side now. Just most important thing is just to remember, am I dealing with a lens or am I dealing with a mirror? Okay, so a converging lens or a convex lens has a positive length for its focal point. So its focal length is positive, and for a diverging lens, its focal length is negative, because this one focuses it on the real side, so it's going to have a positive F, and diverging focuses it on the opposite side. Well, it actually really doesn't focus, it's just where it appears to focus, so it's going to have a negative F. So if I give you a concave lens, you have a focal point of 10 centimeters, it will be a negative 10 centimeters. If I give you a convex lens with a focal point of 5 centimeters, that will be positive 5 centimeters. This is the thin lens equation. You notice it's the exact one that we have used for mirrors. F is for a focal point. DO is the distance of the object. DI is the distance of the image. And for these equations and these practices that we're going to do, most of the measurements are given in centimeters. You can just leave it in centimeters. That is okay. Same thing with magnifying equation that we used with mirrors. Okay, HI is the height of the image, and this is height of the object. Centimeters, okay. So let's do this example. We have an object that is placed 45 centimeters from a converging lens. So converging means they come together, so that is going to be this type of lens, a convex lens with a focal length of 25 centimeters, and that should tell you, remember that is a positive, so the focal point is on the positive side. All right, so that's our F prime, or I'm sorry, F star. Okay, so we want to find the resulting image distance for part A. So image distance will be di. What's the resulting image height? Hi. And then we'll draw a diagram of this. And this is your distance of your object. All right, so first let's write our equation. We're going to solve for dO. Let me see if I can make this bigger. I'll just move it over here. All right, so our equation is 1 over F is equal to 1 over dO plus 1 over di. And we want to solve for the distance of, no, I'm sorry, we want to solve for the distance of the image. Where is that image going to pop up? Our focal point, or focal length, they told us was 25, and remember it's a converging lens, so your object is here, eyeball is on this side, so it will converge on the positive side. That is our F star. This is our F prime. So our focal length, they told us, was 25 centimeters. So that's 1 over 25 is equal to 1 over dO, which was our distance of our object, 45. Oops. 45 plus 1 over di. All right. Now, even though our object is technically on the negative side, your dO is always going to be positive. So don't worry about that. dO is always positive. It's just if your image pops up over here and is, well, it's not going to be upside down like that, but if your image pops up on the positive side, I'm sorry, on the negative side, then it's going to be, your image distance would be negative. But that might not necessarily happen in this case. So when we solve for that, just like with the mirror equation, you should get a 0.01778 is equal to 1 over di, and then you just need to do 1 over that to give you your answer for di. So distance of my image should be 56 centimeters, and remember it's positive, so that means it's going to be a real image, and it will pop up on the same side as the viewer. So this is part A. Let me go to a new screen for part B. Okay, so for part B, we are now going to use the magnification equation to solve for the image height. We're going to solve for the image height, and I just realized I didn't actually give you the height of the object, so we're going to say that the height of the object is 5 centimeters. And now we can figure out how tall our image will be. So remember, our equation is HI over HO is equal to negative DI over DO. We just solved our DI to be 56. So HI is what we're solving for over HO is 5. That wasn't in the original one, but I should have added it in. So we'll say that our object is 5 centimeters. Our DI was 56. And yes, it was positive 56, but with this equation, you have to have, it's a negative, okay? Over our distance of our object, which was given to us, was 45 centimeters. So when you solve that out, you should get the height of the image is negative 6.2 centimeters. Now that tells us that if it's negative, it's going to be inverted, which makes sense because we already said that it has a positive DI, so it's going to be real. So that is inverted. That's for part B. Now for part C, we are going to do a ray diagram to show that we are correct. So we have a converging lens, we have a focal point. This is our real focal point over here. This is the positive side, the negative side. It said that our focal length was 25 centimeters. So that means it's going to be the same on both sides, all right? This is our viewer side. And the object was placed 45 centimeters from the lens. So that means our object is placed past the focal length. So if our object is placed all the way over here, that gives us some knowledge about what kind of image will form. So let's do our drawings. So top of the image straight to the lens and then converges on the other side through the focal point. Second line will go straight through the image this way. And does not look like they will meet, but they will, I promise. They're going to meet on this side because it's really, really far. Remember, with a convex mirror, or I'm sorry, with a convex lens, if your object is is on the other side of F, of its focal point, like very far from it, then it's going to flip everything upside down and create an upside down image. All right, and that upside down image should be larger than the object. If we said the object was 5 centimeters, that's true. So it should be larger, inverted, and real. All right, let's do one more example. We have an object that's 9 centimeters high and is placed 9 centimeters high, placed 27 centimeters in front of a concave lens. So we just did a convex one, now we're going to do concave. Focal length of 18 centimeters, what's the position and the height, and then draw a ray diagram for this scenario. So let's label all of our givens. Object is that high, so that's the height of our object. And it's placed, so that's the distance from a concave lens. Remember that a concave lens is like this. Concave lens focuses light on the same side as the object. Okay, so it's going to have a negative focal length. And it's on the opposite side of our viewer, so they will create negative, smaller images that are virtual. So I want to know what is the position of the image and the height of the image. All right, that's our focal length, and we just said it was negative, so that's going to be negative 18 centimeters. And then we're going to draw a ray diagram for this scenario to make sure our numbers add up. So first, let's solve for our DI and HI. So for DI, right, we use our thin lens or mirror equation. DI plus 1 over DO. You can see right off the bat, if I don't make my F negative, I'm going to get the wrong answer. Okay? All right, we're going to solve for DI, and our DO is DO. What did I just say it was? Our DO was 27. 27 centimeters. Okay, when you solve all of that out, you should get a DI that is negative 10.8 centimeters. Now remember, when the image is negative, when you get a negative image like this, negative distance for your image, then that's going to tell you that it's virtual. Now we will solve for, let me scroll down. Now let's solve for the magnification. So we're going to solve for the height of the image. We'll use our magnification equation, which is HI over HO is equal to negative DI over DO. And we plug in HI over HO, which they told us it was 9, equal to negative DI. We plug in what we just solved for, negative 8, but two negatives make a positive over DO. Distance of our object was given to us as well, 27. So solve for that, and you get a height of an image of 3.6 centimeters. Height of our image is positive, so that means our image will be upright. which confirms what we know to be true about our concave lenses, that they will always create an image that is smaller, upright, and virtual from the object. Let's do a ray diagram just to be sure. Okay, ray diagram for this. I'll do it down here. Let me zoom in. All right, the middle line right there. If our object is, okay, so it said the focal point was a distance of 18 centimeters, then, and our object was placed 27, so our object was still farther out here. Our object was farther than the focal point. So now we do our line. So our first line goes straight to the mirror and then through F. Again, you can do the dotted line if you want to, or just do a straight line. That makes your job easier. And then next one will go straight from the object through the center of our lens, and the object would form right where those two meet right there. So smaller, upright, and it's on the same side as the object, so it is virtual. We're on the other side of our viewer. Okay, this is a great summary slide that shows the difference and similarities between the lenses and mirrors that we have looked at so far in this unit. So first off, when we are looking at our lenses, remember your object is on the opposite side of the viewer. So the viewer, you look through a lens at an object, versus a mirror, you're on the same side. You can't really look through a mirror. That's the whole purpose of it, is everything reflects. So a converging lens and a converging mirror, or a concave mirror. So a convex lens and a concave mirror act very similarly. So again, convex lens and a concave mirror act similarly. Convex lens is like a magnifying glass. It focuses light on the opposite side of it, on the same side as the viewer. Concave mirror focuses light on the same side as the viewer. You can start fires with both of these guys if you have a big enough one. Magnifying glass, right? You can focus the sunlight and focus it on one point because it takes all this light and it focuses it on the opposite side. Concave mirror focuses it on the same side. Diverging lens, everything that comes through is going to get spread out. Convex mirror, everything that comes to the center of it will spread out as well. All right, so a diverging lens or a concave lens and a convex mirror act similarly. All of the light that comes through gets spread out, and these both will create the same type of images. They will create smaller, upright, and virtual images that are always going to be virtual. Okay, smaller, upright, and virtual. They make things look smaller. Versus a convex lens and a concave mirror, they can do it all. They can do real and virtual images. All right, depends on how far away you are from the focal point for each of these. Okay.